Alright, so this lesson is going to be the answer to the question, why did we bother learning about implicit differentiation? So this lesson's about related rates. So first, maybe some understanding. What are related rates problems? Well, related rates problems are problems that involve related quantities, where the quantities are changing with time. The thing that we're interested in is the rates at which these quantities are changing. So how quickly they're changing or what their values are changing at. All right, so let's kind of start off with an example of something we could think about that could help us understand where related rates are coming from. So imagine you're blowing up a balloon. Some things that might be changing about the balloon as you blow it up, assuming it's got the shape of a sphere, are the radius, the circumference, the volume, and the surface area. All of these are increasing. So the rate of change is positive. However, if the balloon was being deflated, they all would be decreasing or have some sort of negative rate of change. Now let's say you instead were pouring yourself a cup of coffee, a coffee mug. There are certain quantities that could change as you're pouring. The mass of the coffee, for example, that is in the cup. The height of the amount of coffee that's in your cup. The volume is going up, and these are all positive rates. And if your coffee cup happens to be shaped like some sort of inverted cone, you also have the radius changing. So in these related rates problems, our idea is going to be to compute the rate of change of one's quantity in terms of the rate of change of some other quantity. And typically that other quantity we're looking at is something that we can measure a little more easily. So we will start with an equation that relates the two quantities, or the quantities that are changing. And so, of course, in order to then go ahead and talk about their rates, we have to go ahead and differentiate. So then we differentiate to obtain an equation relating their rates of change. And so again, the key to all of this is implicit differentiation. Alright, so recall that when we're talking about implicit differentiation, we're often having to use the chain rule. So when we're talking about taking the derivative of with respect to x of y squared, we have to keep in mind that y is some sort of function of x. So when we do this, what we end up with is using the chain rule, 2y, so the derivative of this would be times y prime. Or we can think of this as 2y times dy dx. So that's the rate y is changing with respect to the variable x. In related rates problems, oftentimes our quantities are going to be focused on time, and so our variable will be t. So suppose we've got some radius that's changing with time, then the derivative with respect to time of r squared will follow the same thing. We'll do the power rule and the chain rule here, so 2r times r prime, which again we can think of as 2r times dr dt in this case, because t is our variable. So in this case, dr dt is the rate at which the radius is changing with respect to time. Alright, so let's go through a few examples. So say we've got some air being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. We want to know how fast the radius of the balloon is increasing when the diameter is 50 centimeters. And one thing we're going to remind ourselves is that the volume for a sphere is V equals 4/3 pi r cubed. Alright, so there's a lot to unpack here. So let's kind of just take it a step at a time. First, let's go ahead and look at the quantities we have changing with respect to time and assign some symbols or variables to them. So we know that we've got the volume of the balloon, V. We also have this radius, so that's r. Alright, so next we want to go ahead and kind of split our information into some information that always works, or works in general, or particular, or it only is true about a particular instance in time. So our goal here is to find rate at which the radius is increasing given that the diameter is 50 centimeters. So in general, we know that regardless of what the centimeters is, or regardless of the time, the volume is increasing at 100 centimeters cubed per second. So here this rate is something that's going to be general, and our rates are always going to end up being general. So that's the thing that we're going to have that we can kind of hold on to. In particular, we're saying that we're looking at this specifically when the diameter is 50 centimeters. So we'll come back to this later on in the question after we've gone ahead and kind of done our differentiation. So we want to write an equation that relates the quantities that are changing with time. Fortunately, we already have that. That's given to us. Volume equals 4/3 pi r cubed. So next, we'll go ahead and differentiate both sides with respect to time to get an equation that relates their rates. So we'll take are both sides of the equation. And we want to differentiate this with respect to time. Using the chain rule on the left, we'll get 1 times dv dt, or just dv dt. And using the chain rule on the right, what we'll end up getting is the derivative of this times dr dt. So we'll get 4/3 times pi times 3r squared times r prime. Or in other words, we can rewrite this whole thing as being dv dt equals, once we cancel out these 3's, 4 pi r squared dr dt. So this will be the equation we have now that relates what those rates are going to be. So at this point, we want to go ahead and take the information we have and this equation to try to use what we know. See if I can find a way to get this all on the same screen. There we go. So things we know are that the volume is changing at a rate of 100 centimeters cubed per second. And we know that in this particular problem, the diameter is 50 centimeters. But we don't actually care about the diameter, we care about the radius. The radius, remember, is just half the diameter. So this tells us then that the radius is 25 centimeters. And we want to know dr dt. So in that case, what we'll do is we'll just take this equation and plug in the things we know. So if dv dt equals 100 centimeters cubed per second, then on the left we have 100 centimeters cubed per second, and on the right we've got 4 pi times 25 centimeters squared times dr dt. So that's just plugging into what we have in this equation. And so now, if we wanted to go ahead and try to solve, what we'll do is we'll divide both sides by this 4 pi times 25 squared centimeters squared. And so as we look to find what our units end up being here, the centimeters squared will cancel out with some of these centimeters cubed, and we'll just go up with centimeters in the numerator and seconds in the denominator. So we should end up with 1 over 25 pi centimeters per second equals dr dt. So that means the radius is changing at a rate of 1 over 25 pi centimeters per second as at the time when the diameter is 50 centimeters. All right, so let's say we want to go ahead and understand the steps for solving these related rates problems in general. The first step, and this is always the first step in every problem you'll ever face, don't panic. These are complicated things, but panicking is usually the sure way to go the wrong direction. Start by trying to draw a picture if you can. Second step will be to try to identify all and assign all the symbols to all changing quantities. So anything that's going to change in this problem, you want to make sure you've got a symbol for and you understand what it is that's happening. Next, you'll want to go ahead and separate your information into what you know in general and what's particular to this problem. So in our case, we said that 50 centimeters as the diameter was something that we were looking at. So typically, the particular information is things that are only applying at some particular time. It can be helpful in this step to write a goal statement. So that way you can keep track of what it is you are trying to find. It also is something where you can try to plug in any general information, only the general information. And I want to focus on just the general. Before you take the derivative, however, you should never plug in particular information before taking the derivative, because that'll usually cause some parts of your derivative to not behave the way you need them to. Now, after you've done this, you'll want to make sure you get an equation that relates these different quantities that are changing with respect to time. This is not where you take the derivative yet. The derivative is the next step. So once you have your equation that relates things, you can take the derivative with respect to time using implicit differentiation, so you'll have a lot of chain rule things happen, and this will help you obtain an equation relating the rates. Then you should organize the information of things you know and things you want to find. You can go kind of refer back to your goal statement at this point, and make sure that all of your units match properly. Sometimes you'll have to convert units in problems, so do not forget to do that. And then last but not least, you want to plug in and solve for the thing you don't know. And don't forget that at the end of the day, the units are very important. All right, let's go through a few more examples. So say we've got a 10-foot long ladder that is resting on some sort of vertical wall. If the bottom of the ladder slides away at the rate of 1 foot per second, we want to know how fast the top of the ladder is sliding when the wall, down the wall when the bottom of the ladder is 6 feet from the wall. So first thing we're going to do, step one, is not panic. We also can try to draw a picture of this, that way we can understand all the things that are happening. So we've got this wall here. It's a nice wall, it's a lovely wall. And we have some sort of ladder. We know that the ladder is always going to be 10 feet long. Nothing about that's going to change. We have our y and our x. So here the x is where the bottom of the ladder is resting at, and the y is where the top of the ladder is resting at. We know that as we keep going, the bottom is sliding away at a foot per second. What we don't know is how quickly the top of the ladder is coming down. Alright, so the second step is to go ahead and make sure we identify all of these quantities that are changing. So again, we've got y, which is the height the top of the ladder is from the ground. And at this point, we expect this to be decreasing. And x, which is the distance from the bottom of the ladder to the wall. And not only do we know this, but this is some sort of increasing rate. And we know the rate at which this is happening. So next, we want to go ahead and separate our general and particular information. So our goal is to find what rate is y changing at when x equals 6 feet. So when the bottom of the ladder is 6 feet away from the wall. So, again, our general information here, things that we know is that our rate of change for x with respect to time is 1 foot per second, and we know that the ladder is 10 feet in length. The particular things we know is that for this problem, we're saying that x equals 6 feet. Now, because this is particular, we can't plug it in until after we've taken the derivative. So next, if we know what we've got here, we want to know what sort of equation we can have to relate these. Now, what you might have noticed is that this is essentially a right triangle. So, since we have a right triangle, if we know our Pythagorean theorem, we can relate the length of this side, the length of this side, and the length of this side. So we know then that x squared plus y squared equals 10 squared. Because 10 is the length of the ladder. So 10 squared, of course, is just 100. And so in our next step, we want to go ahead and take the derivative. So we want the derivative with respect to time of x squared plus y squared, and set that equal to the derivative with respect to time of 100, which remember is just 10 squared. Alright, so on the right, the derivative of a constant is just 0. On the left, we have to take the chain rule for both of these. So we'll have 2x times dx dt plus 2y times dy dt. Alright, so at this point, we want to go ahead and take stock of what we know. So remember, we know that dx dt is 1 foot per second, and we know that x equals 6 feet. The thing we want to solve for in this problem, though, is dy dt. And so the only thing we don't have that we could really use is y. So we're going to need y in order to figure out how to solve for dy dt. Well, fortunately, we again just have the equation of a triangle. So if this is 6 feet, and this is y, and this is 10 feet, then following along with how we do the Pythagorean theorem, we'll have 6 squared plus y squared equals 10 squared, which tells us that 36 plus y squared equals 100, which tells us that y squared equals 64, which tells us that y equals 8 feet. So we can use this then with our last step, which is to go ahead and plug in. So taking this equation and plugging in the things we know, we'll have 2 times 6 times 1 plus 2 times 8 times dy dt equals 0. So multiplying through, we'll get 12 plus 16 dy dt equals 0. We'll subtract over, so 16 dy dt will equal negative 12. And then dividing both sides by 16, we'll end up with dy dt equals negative 3/4 feet per second. Feet per second. Which we expected it to be negative because we know that y should be decreasing. So that matches up with what our expectations are. All right, let's go ahead and try another one. So now say that we've got a car that's traveling west at 50 miles an hour and another car traveling north at 60 miles an hour. If they're both headed for an intersection, we want to know at what rate the cars are approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection. Okay, so a lot to unpack here. Again, step one, don't panic. Let's go ahead and draw some sort of graph. So we know car A is traveling west. So here's A. A is going this way. And A is traveling at 50 miles per hour that way. We know that B is heading north. So B is over here. B is going north. And they're both approaching some sort of intersection. B is going 60 miles per hour. So we know that we've got A and B as these little a's and little b's are going to be our distances that they are from the intersection. But we want to know how quickly they are approaching each other. And so that is actually going to be a third distance, C. Now, because of the way these west and north are working out for us, we get another right triangle. So next, we want to look at which quantities are changing. So we've got little a and little b. So little a is the distance car A is from the intersection. Little b is the distance car B is from the intersection. But this little c here is the distance between the two cars. Now note that all of these distances should be decreasing. So all decreasing because they're getting closer to where we're going. So our goal is to find the rate at which little c is changing. So if we're getting closer to the intersection, these 50 and 60 miles per hour should be negative. So in general, we know that d little a dt is negative 50 miles per hour, and dB dt is negative 60 miles per hour. In particular for this problem, so we can't plug it in yet, we know that little a is 0.3 miles and little b is 0.4 miles. So again, we now are going to need an equation to relate all of these. And so here we have a triangle, so again we'll take a squared plus b squared and set it equal to c squared. And our next step will be to differentiate on both sides. So we want the derivative with respect to time of a squared plus b squared. And we want to set that equal to the derivative with respect to time of c squared. So again, we want to use the chain rule, and so we'll get 2a dA dt plus 2b dB dt equals 2c dc dt. Now, we want to think about the things we know versus the things we don't know. So we've already know that dA dt and dB dt are given, and we know for our particular problem little a and little b are given. But what we don't know is little c, when little a equals 0.3 and little b equals 0.4. Fortunately, we again can use our Pythagorean theorem to try to find little c. So 0.4 squared plus 0.3 squared equals c squared. And if you go through all the steps here, this will end up showing you that little c ends up being 0.5 miles. And so last but not least, we'll go ahead and plug in. So we'll have 2 times 0.3 times negative 50 plus 0.4 times negative 60. Oh, forgot the 2. 2 times 0.4 times negative 60. And we'll set this equal to 2 times 0.5 times dc dt. Well, 2 times 0.5 will just go ahead and give us dc dt. So on the other side, we just need to go ahead and plug things in. So we got 2 times 0.3 times negative 50, which will give us negative 30, plus relationship between sine, cosine, and tangent in a right triangle. So if you remember your things from SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Those are things you should know. The formula for the distance between 2 points. So if you want to relate the distance between 2 points, that distance is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Any sort of easy volume formulas, say if I've got some sort of rectangular prism, you should know that volume. And other easy area formulas. So if you want the area of a square, area of a rectangle, a circle, those are all things you should be able to know without me giving them to you. However, there are some formulas that you might need and will be given to you if you end up needing them. So, for example, the volume of a cylinder is equal to pi r squared h. The volume for a sphere is given as 4/3 pi r cubed, and the volume for a cone is 1/3 pi r squared times h. So, a little bit of a checking to see how well we've been following along and making sure we understand all the things we need to do. Say we've got some gravel being poured into a canonical pile where the volume is changing with time. So canonical meaning cone. As a result, the height and radius are also changing with time. We know that at any particular moment, the volume equals pi over 3 r squared h. So that's just a different way of writing this formula. We want to know how that relationship between the changes in the volume, radius, and height with respect to time looks like. So take a minute, see if you can figure out how to take this derivative and find out which equation is going to be. And then after you've done that and unpause the video, come back and see if you were right. Alright, so we're looking at taking the derivative with respect to time on both sides of this equation. So we've got volume on one side, and we've got pi over 3 r squared h. And we don't care so much about the pi over 3 because this is just a constant. We can pull that out to the front. However, the r squared h, both of these are things that are changing with respect to time. So because of this, we need the product rule. And so on the right, real easy. It ends up being dv dt. Sorry, on the left it's easy. On the right, we're going to pull this pi over 3 out front to make our lives a little bit easier. And we'll multiply it by the derivative of this. So we want to take we'll take the derivative of this first. So this will be 2r dr dt. And we'll multiply it by the h we have. Plus, we'll have our r squared times the derivative of the h. So this will just be dh dt. So at the end of the day, we end up getting b as this way of describing this rate of change. So again, all we have to do is take that derivative, and now from here, if we had other known things and wanted to solve for one, we could plug those things we knew in and go ahead and do our solving.